This tutorial is actually sort of a hello world of machine learning coding example. And we're gonna use the deep learning machine learning library keras in order to do a first digit recognition, digit classification example. So this is based on the traditional MNIST dataset, and therefore sometimes considered the Hello World coding example, the first introduction to machine learning. Okay, so so what do we want to do? We want to the MNIST dataset consists of digits 0 to 9, and the idea is like small images, for example, for postal code recognition or something. And we want to be able to build a classifier network that is able to solve this multi-class problem, to assign an input to a digit from 0 to 9. Okay, so we start with loading keras library. Oh yeah, library. Okay, so keras installed now. We can load the dataset, MNIST dataset. And as you can see, keras comes already with several of these traditional famous example datasets. And as a small explanation, as you can see here, we got this dataset of 60,000 28 by 28 grayscale images of 10 digits, along with the 10,000 images that we use for testing. Okay, now I want to load it. So once loaded, we do set this part into, as you can see, let's do the following. Let's load this so we can access it actually. Oops. Oh, it's still loading. I was a bit too eager here. I didn't realize it's that big a data set. Okay, now we're there. Okay, so going one step back now, you see this already separated into train and test, and that's pretty convenient here. Since it's also separated within each group into X and Y, that makes our data and our labels in the, yeah, let's do this to have this a little bit more general. So what I actually like, some formalization, something like this. Kind of have a standard way of writing this. Okay, and then this is our test data. Yeah. Okay, so that's now, we've been separating these. Okay, now we could have just a brief look at what we got. As I've mentioned, we've seen what we were expected to have here: 60,000 examples of 28 by 28 images, grayscale, and basically, if you will, 60,000 arrays, right? So, and this is actually, sorry, that might be a little bit misleading. So basically this is a representation of a 3D array, and then basically here we have the number of, if you will, individual 2D arrays, right? So each image, each grayscale image basically constitutes a 2D array, and then we can put this nicely together into this nice tensor representation. Okay, yeah, so Now let's define a very simple first network. So this is our network, and yeah, let's do it like this. So we add, as you can see, this is the function called keras module sequential, and here's the explanation already gives it away. We define a keras model that will be composed of a linear stack of layers. So that's what we start with. Now we have this keras specific syntax, right? Of okay, how do we add additional layers to the model? So this first thing was basically just to say, okay, we want to build this sequential model. Now we define our model. So first thing is, and then basically, or this is where we actually can make our customizations here. So, oops, let me write this activation. Okay, so as you can see, what we're doing here is we're building dense layers here. So this is very just a very simple initial network, and we might later see the beneficials of using, for example, a convolutional neural network for this particular approach. But here we start with this example. So, okay, so we define the first layer as with input with 8 units, with 512 units. We give it an activation function on how to basically integrate the results and an input shape, right? So this is actually for the first layer, having a correct input shape that corresponds to the actual shape of the data is essential. Okay, so, and then we continue, say, okay, we'd love to get another layer, and here, given this is a very simple example, we say, okay, this is basically now our output. So the number of units is basically the number of output units, and therefore we set it to 10 because we got 10 digits to classify. And now, yeah, what we need to also define is the classification function, and traditionally we use the softmax classifier, right? Okay, so this is basically the definition of a network. Now we need to compile the network. How do we do this? We basically continue, using the compile function, and okay, we set an optimizer. For our purpose here, this is not as important what we choose, but let's go with something like the RMS prop, and we set a loss function, and here we go with the categorical cross entropy. So categorical, given that we have actually, it's not just a binary classification problem, right? So here we have 10 classes, so it's a multi-class problem with actually, if you will, 10 categories that we want to distinguish. And of course we need a metric. Okay, let's go with accuracy. Okay, so let's see if we did all of this right. We'll see in a sec. Yeah, we'll see later. Okay, so we should be able to run this part already. Okay, so there's no error here. Yeah, so one more thing we're gonna do is to reshape our input array. So let's see, basically reshaping it, given that we're not dealing with it's going to be interesting. Here we're going to reshape our 3D array into 2D array because as you can see here, we basically are not working with a, it's not to be confused with a convolutional neural network that takes as input individual images. This actually takes as input sequences. So in our case, since we have a width and height of the image S28, the input vector is basically width times height, and then the image is transformed into this vector of pixels, if you will, and that's actually what we're going to do now. So we take our three-dimensional input image, I'm sorry, three-dimensional input array of training samples, and we turn this around into this two-dimensional. Let's see, maybe we can, here you go. So this is how it looked like, and now we're going to do this. Take a few seconds. Okay, and now we just have a look at this, and as you can see here, right? So this has basically been from a three-dimensional array of individual 60,000 two-dimensionals. Now we have this array of 60,000 individual vectors of length 784. So we, of course, we need to do the same thing for our testing data. And okay, whoops. Oh, what's going on here? Let's see. Cannot reshape. See, what is this? Oh, of course. Okay, here you can see what's gone wrong. So actually, this is a bit misleading. One, yeah, I should have been. Okay, I just made an error copying this. Of course, we only have like a stick of these examples. Okay, and then there's one more thing that we're going to do is to basically reset the range. So as I've been saying, these are grayscale values. So the rays have a maximum value of 255, and we're basically normalizing this in a range of 0 to 1. It's also something always when doing the classification, we need to make sure that our input and output are kind of normalized in a reasonable range, and actually equivalent ranges across features. Okay, so one more thing we're going to do with respect to the labels is as follows. As I mentioned, we have a categorical problem, so we turn this into the representation. Okay, and that actually can be done by using two categorical. Getting this one hot encoding representation. Let's do the following to visualize this as well. So here, this is actually, as you can, oops, now I was thinking in Python. Okay, so here we got our 60,000 labels, and okay, so as you can see, if we label this, okay, here's summary. You can see there's like sort of equivalent numbers of each digit, and it's really the label is actually the digit itself. Now this is a bit difficult for a multi-class classifier, so we're going to do the following. And you see, this is what we get. We get this one hot encoding representation. So this is a training sample, and then basically, since we have 10 categories, this is what we have, and we get a single one at the position where we had and what the label actually is. So as you can see here, so it starts with 1 here, so it's a little bit confusing. This is actually the 5, and if you follow through with this, you can see that basically we get the corresponding ones set at the position. So this should actually be 0, 1, 2, 3, 4, 5, blah blah blah, up to 9. Okay, so this is the one hot encoding representation, and that is all for data preparation at this point. Okay, now we can do the following. We can start evaluating our classifier. Yeah, so let's go with our network and let's do an evaluation. And oh, I'm sorry, evaluation. Okay, we first need to, of course, train our classifier. So let's comment this out. Okay, so now we're all set to fit our model. And therefore we take our training examples and we take our training labels. And yeah, here we say, okay, how many epochs do we want to train, and what should the batch size be? Okay, and let's see what happens. Okay, so yeah, here we're running on CPU. I mean, for this particular small example, it's not as important. I'll look into other tutorials on using GPU or using cloud platform, but here we are running this on our local GPU, and we're almost there. Or maybe we can already prepare the evaluation part. For the evaluation, we take our test images. Oops, this should be X tests. Oops. So, okay. Now let's evaluate. Let's have a look at the metrics. Boom. Okay. So again, since we're using accuracy here as our metric, this is what we actually get. Yeah, now we can use this model to do predictions. Yeah, just to give one final example here. Let's do predict classes, and let's take this and just take a few examples. So basically picking out the first 5 examples here, doing a prediction, and okay, if we can check it. Oops, no, that's not what I wanted. Okay, now we've been in this one hot coding. Oops, oh, my mistake. Okay, let's do something here. Oh yeah, that's nice. Let's pick this up. Gonna violate my, okay, and so here we go. This is again labels of the testing data set in the original representation, and here's our prediction. As you can see, in this case they do match. So yeah, even without using a convolutional approach here, just going with this sequential approach, this MNIST data set can be solved pretty neatly. Again, if we're going to later look at an intro example for convolutional networks, and taking on the MNIST, and we're going to see that accuracy increases, given that this making use of these spatial representations here.